Okay, so you should have just completed the first part of the Combine exercises. And so we're just going to discuss a couple of the questions that we asked. So one of the things you did was adjust the magnitude of the uncertainties in your data card. And what you should have found is that when you make the uncertainties smaller, so the percentage uncertainty smaller, you should have found that the limits get stronger, i.e. the values themselves become smaller. And conversely, when you make the uncertainties larger, the limits should get weaker. And this kind of makes sense. This kind of is what we'd expect to happen. So the more uncertainty we have on our signal and our background expectations, the weaker our limits, so the less we should be able to say about the presence of any signal. And so it's important to remember then, so a higher value of the limit is less stringent. And so what you can see on the figure on the right is an example of what the kind of limit plot that we typically produce in CMS. So this shows the limit as a function of the mass hypothesis here, m phi. And so we were just looking at one particular fixed value of the mass shown by the red dashed line. And so here you can see all the same information that we were looking at. So the observed limit given by the black solid points, and then the expected limits, so the median expected given by the black dashed line, and then the 68 and 95% intervals for the expected limit given by the green and the yellow bands. So then another thing we did is looked at what happens when we change the number of observed events in the data card. And what we found is that actually this also changes the expected limit. And at first, this seems like a little bit counterintuitive, perhaps, because we might ask, well, what does the observation have to do with the expectation? But actually, in the procedure that we use, the expected limit is determined after performing a fit to the data, a fit to the observation. And so in that fit, if you like, our background expectation might be adjusted up or down, and this itself directly affects our expected sensitivity for any signal. So actually, this is fully a fully normal feature of the limit setting. But sometimes you will actually want to avoid using the data at all. So not even performing this fit to the data for the expected limit. And so you're going to learn about this in the next part, which is part 2, which you can start now. Okay, so in the second part of this tutorial, we're going to look at shape-based analyses. So you're going to create a data card for a shape-based analysis. There's an example given at the bottom of this slide. So not exactly the example you're going to be using, but it shows some of the main features. And so you'll notice that this looks a little bit different to the counting experiment data card from the previous section. So two main things that are different. So the first thing you can see in the first red box is below the Imax, Jmax, and Kmax lines. We have these additional 2 lines that start with shapes. And so these are, if you like, sort of mappings. They map from particular combinations of process name and channel name to root files, and then objects within those root files, which will usually be histograms, so TH1 objects. And so you can create these shape lines specifically for the root files that you have in the example. And just to give an important hint at this point, so in this example here, for example, you can see the second line refers to a signal process that's called signal. In the data card that you're going to be working on, the signal process is not called signal, it's called something else. So you need to take that into account when you're constructing your own shapes lines for your data card. And so the second thing that's new is you can see at the bottom, now we have a shape-based analysis, so considering an actual distribution, an actual set of bins. We're not restricted to just uncertainties that affect the normalization. We can also have systematic uncertainties that change both the normalization and the shape of our signals or our backgrounds. And so we can do this by writing this shape systematic uncertainty instead of log normal. And one thing we also have to add is additional histograms into our input root files that give the shapes of the distributions when they're shifted by ±1 standard deviation with respect to that uncertainty source. And so there's more explanation of this in the tutorial, which we recommend you read through and have a look through. So after creating the data card for a shape-based analysis, there are a few other tasks to work on. The first is to see how the limit changes compared to the cut-based analysis. So do we see an improved sensitivity by using the shape information? And you'll also see how to perform a blind analysis, so what you can do without using the observed data. And then we'll switch from setting limits to actually performing measurements of parameters. And you'll do this using a method in Combine called fit diagnostics. Next, we'll consider another important type of systematic uncertainty that you need to add to your analysis called Monte Carlo statistical uncertainties. And we can see how that can be easily achieved with Combine. And then finally, we'll try and delve a little bit more into understanding how our different uncertainties represented by nuisance parameters actually affect the sensitivity of our measurements. And we'll do this by calculating what are called the nuisance parameter impacts. So this looks at the shift in the parameter of interest, so in this case our signal strength R, that's induced as the nuisance parameter is fixed and to its best fit value, and then shifted between its post fit plus minus 1 sigma values. Okay, so have a go at these exercises and then watch the next video where we'll discuss some of these points.